So our next speaker is Neel Pandeya from National Instruments. He is a principal SDR engineer and group manager at NI. He has various interests in open source software development, 4G, 5G, DSP signal processing, FPGA, and so on and so on. Well, he's also very active in research. So he's a co-founder and organizer of New SDR and also co-organizer of GNU Radio Conference and the 5G workshop at the IEEE Milcom. He is or has a master's degree in electrical engineering here from Northeastern University. So he's at home apparently to some extent. And yes, he's also, or he has a amateur radio license. And yes, thanks. And he will now speak on unlocking the potential NI's vision on wireless innovation in OAI. Thanks.
Great, thank you.
Thank you.
Hi, everybody. Thank you. I'm here today with my colleague, Dr. Amr Haj Omar, who's in the corner there. And we'll talk about 6 different things and touch upon updates at National Instruments regarding the USRP and some of our wireless activities. So first, I'll talk quickly about the USRP X440. This is based on the X410 radio that you might already be familiar with. The X410 is our newest series of radio, the X400 series. It's based on the Xilinx RF-SoC chip, and it has a frequency range of 1 meg to 8 gigahertz. You can tune to 7.2, but you can actually tune beyond that, up to 8, and it provides 400 meg of bandwidth per channel. So this radio forms a platform, so the motherboard serves as the baseline for a bunch of other radios, the first of which is the new X440. And the X440 is a baseband radio that we've introduced at GNU Radio Conference 2 months ago. And it is a baseband device that provides 1.6 gig of bandwidth, baseband bandwidth per channel. You can have up to 2 channels at full bandwidth, providing 3.2 gigahertz total. And the tuning range is between 30 meg and 4 gigahertz. So this is our newest device. It's also based on the Xilinx RF-SoC, uses the same motherboard as the X410 radio. And provides phase coherence and a GPS receiver, GPS-DO, internally. Next, I'll talk about the reference architecture and testbed. This has been a long-running project at NI. We basically provide a reference architecture and an application note and documentation to steer the user, guide the user through the process of building a 5G network using the OAI software stack on a variety of USRP devices like the X310, the N300 series, and the X410 radios. And this architecture walks the user through how to build the core network, how to build the G-Node B, and how to pair that with different UE implementations, whether it's a OAI rather, UE running on a USRP device, or a handset like a Google Pixel handset, or a Quectel or Sierra Wireless modem module device. And this reference architecture is posted on our knowledge base. And so you can go through that and build a system and have sort of a known good starting point to use the USRP to implement a 5G system. This is one example we have of the system with for FR1. This is what's documented right now and has all the requisite components and different varieties of the UE. You can see the configuration listed in the top. That's one of the configurations featured in the documentation. We're expanding this to FR2 with our partners TMY-Tech and All Be Smart, who makes the OAI box. And so we use the OAI box and the TMY-Tech hardware to support FR2, as well as now FR3, using the USRP X410 radio. This will be added to the documentation shortly, and so users can take that hardware and walk through the whole process of building a system like this. The OAI box looks like this and is paired with the USRP X410 and is connected to the TMY-Tech hardware in the middle there. And the TMY-Tech hardware consists of a UD box, up-down converter box, and a B box, which does the beam forming. And so you can build FR2 and now FR3 systems using these components. Next, I'll talk about the ORAN ORU based on the X410. We are taking the X410 radio and making a software-only change to it that allows it to perform the functions of an ORU. And so the same hardware that you would have now can be used with a new FPGA image and a new software upgrade. And all of the lo-fi functions get implemented on the FPGA. The FFTs, the IFFTs, cyclic prefix insertion and removal, come over to the hardware on the X410, and an eCPRI interface connects to the DU. And so we're in the process of releasing this by December, and by January you should be able to access this. This will be open sourced as well, and so you can see some of the specs there in terms of the C-plane and U-plane support. The interfaces right now initially will support 10 gigabit Ethernet, which will allow for a 100 megahertz carrier. Later we'll have the 100 gigabit Ethernet support. So this flavor of the X410 is coming in January, and there'll be successive releases later in 2024, adding more capability. Next, I'll talk about some AI ML updates that we have. We talked about some of these at the NI Connect conference back in May in Austin, Texas. And this is done in partnership with Professor Kaushik Chowdhury here at Northeastern, who's in the picture in the middle. And the motivation here is to think about how best to embed AI into 5G and 6G systems, and what are some of the challenges. And one challenge that we've identified is data, as well as test and a few other things. But the data part makes us think about the applications of AI, ML, and wireless. And we're probably familiar with a whole bunch of these, and where AI and ML can play a part and improve system performance. One of the things we found is that data is one of the key inputs, and getting, there are a couple of challenges. Getting a high quality data set is a challenge. Often when you collect data sets, the file formats you use are not standard, and they may not include a lot of metadata and other hierarchies that are needed to preserve and organize that data, or share that data across teams, across groups. And it's often tedious to try to collect this data. It's very time consuming, and it's something that generally is not easily done. So we partnered with Northeastern University, and we created the AI ML RF data recording API. This API is open source. It's available on GitHub. And basically, it provides a Python-based interface to the USRP and a series of tools that allow you to automate the collection of this data. More specifically, you can define waveforms for transmit, waveforms for receive, and you can define things like sample rate and channel and configuration of the radios. You can control looping and iteration. You can control ping-ponging or selection of channels, and orchestrate all of this through a series of configuration files. And those configuration files are defined in JSON or YAML. And so you define a scenario, and on the right, you define a scenario using JSON and YAML, just human readable text files. And then you run that, you make the requisite cable connections here with different radios. The X310, the X410 are supported, as well as other radios, other USRP devices. And then you can run that configuration. And then the output, as it runs, on the right, you'll see output in the console window. And then on the left, you'll get SIGMF data files generated from that. SIGMF is a standard data format for recording IQ data. And so you'll get this data organized in a hierarchy and annotated with metadata like the sample rate or the gain value that was used or the tuning frequency. Other notes may be about the location or the GPS coordinates where the data was collected, metadata about the context of the collection, any other notes you want to add. All of that can get added and put into the SIGMF file format, which is read by many, many different tools. So it'll generate all of that data and dump that for you. And you'll see some of the details here that you'll get a data file and a metadata file. So sort of two files for each data set. And you'll get a series of data sets. And then from that, you can take that and very easily share it with people or archive it and come back to it later. And you have all the data, all the metadata for the context of what you were doing at that time for that data collection. And you can build very large data sets doing this and very easily, just based on configuration files. And then finally, a few updates on the UHD device driver. We released UHD 4.5 2 months ago in September at the GNU Radio conference, and it added support for that new X440 radio that I profiled at the beginning of the talk. It also introduced a few new FPGA configurations for the X410 radio that provide additional connectivity options. And there were numerous bug fixes that we made across devices, a lot of bug fixes in the 4.5 release. And then in 2 weeks, we're expecting to release UHD 4.6. That will bring DPDK 22.11 support, so a much newer version of DPDK. And there'll be bug fixes for the X410 and some enhancements for the X440 radio that we released just 2 months ago around phase coherence and sampling rate flexibility. So those are some of the things happening with the UHD driver. And that's it. Any questions? Okay, thank you. Oh, yes.
So a couple of slides ago, first of all, thank you for the presentation. A couple of slides ago, you were talking about the open API to collect the data, right, for AI and ML. So just what type of data? I understand that it's configuration, right, that you are trying to optimize, I guess. What type of data is collected through those APIs? Is it like alarms, logs, what?
All the IQ data you're recording from over the air, as well as other metadata. So you can annotate the data for things like, the sampling rate that was used or the gain value that was used and things like that. So it's a way of automating the collection of data and cataloging it.
Cool. Yeah. Thank you.
Yeah, thank you.
I had a quick question as well. You mentioned, oh wait, my bad. All right, I'll continue. You mentioned using 440 to set up 5G test beds. Is that easily interchangeable with like a B210? Something of older generation?
Yeah, to some extent. The B210 has some limitations in terms of sampling rate and bandwidth and things like that. But yes, you can use a B210, and that is discussed in the document.
Makes sense. Okay, thank you.
Yeah. One more question, I think, back there?
Yes, thank you, Neel. My question is that FPGA-based RU emulator, will it be only support by the X410, or do you plan to extend support to other radios?
At this point, just the X410, but we are thinking about expanding it, both to old radios and actually some new radios coming out next year. So, yeah. Yeah. Thank you, Eugenia. Thank you. Okay, thank you, everybody.
Thank you.